Let's talk about Bayes' rule today. In order to really understand the idea, we can start with the law of total probability. Intimidating? Don't worry. Take a look at this Venn diagram. We have a sample space S and an event A. Let's now split the sample space into disjoint sets that don't overlap with each other. We call that a decomposition of a set, and as you can see, A is also split into nicely separated parts. Without going into precise definition, let's jump into what this situation tells us. Intuitively, the portions of A that belongs to each set, B's of 1, B's of 2, and B's of 3, makes up the entire thing. Therefore, when we talk about the probability of the event A occurring, we can rewrite it as the probability of A equals to the probability of A and B's of 1, or A and B's of 2, or A and B's of 3. And because these are the disjoint sets, it simplifies to the sum of each of these probabilities. So, how does this transfer to Bayes' rule? Let's recall that the probability of B given A is equal to the probability of B and A divided by the entire probability of A. Using this, for example, we can find the probability that we were in B's of 1 given that A has happened. Intuitively, we can see that it is just this portion that it is intersection of B's of 1 and A, divided by the entire A. Know that because we know that A can also be seen as a partition, to obtain A we simply need to add up all these individual pieces together to form A. Generally, Bayes' rule is stated as such. Why would we do that though? It looks like there is extra work to find such a probability. It turns out there is a situation that the conditional probabilities are easier to calculate than the probability of the entire event. Let's take a look at an example. A bag contains cubes and pyramids that are red or blue. 40% of the shapes are red. Of those, 30% are cubes, 70% of the blue shapes are cubes. If you randomly pull out a shape from a bag and it is a cube, what is the probability that it is blue? Now, to tackle this problem, let's intuitively think that the majority of the color is already blue. On top of that, only a small portion of the red shapes are cubes, so you would imagine that it is quite likely to have a blue color if you know that you pulled out a cube. Let's confirm that numerically. 40% of the figures are red, so the rest must be blue. Of those red, 30% are cubes, so the rest are pyramids. Here you can calculate that the probability of having a red cube can be calculated as the probability of R times the probability of C given R, which is equal to 0.4 times 0.3 equaling 0.12. Using the similar process, we get the following. For organization, we can draw the probability tree as such. Now, let's get back to answering the question, the probability of getting a blue given that it was a cube. According to Bayes' rule, we have the following. Or plugging the numbers 0.42 divided by 0.42 plus 0.12. What's important to note here is that the probability to pull out a cube is actually not available until we calculate it. However, once we do that, we simply combine the law of total probability and the conditional probability in order to calculate the probability we are looking for. That's the basic idea of Bayes' rule. Also note that, as suspected, nearly 80% it would have been a blue because we knew that it was a cube. Let's work on a slightly more complicated example. An airport categorizes the airplanes as 60% from a major airline, 30% from a private flyer, and the rest from a commercial airline. When a passenger uses a major airline, 50% of the time it is for business purpose. Similarly, the proportion of passengers that uses the plane for business purpose is 60% for private planes and 90% for commercial planes. Suppose that a random passenger comes out of an airplane. What is the probability that the person used a private plane given that the person came for business? First, let's gather the information that we are given as such. From our given information, we can calculate each of these entries one by one. Just as an example, the probability of B and M is equal to the probability of M times the probability of B given M, which is 0.6 times 0.5, equaling 0.3. As you can see, using a table is another option to organize your information that helps you visualize the situation. Now, let's answer the question by finding the value of probability of P given B. Bayes' rule tells us that the probability of P given B is all this messed up fraction right here. You can, of course, plug in all the values blindly and calculate the result, which is not a problem at all. However, if you recall where Bayes' rule were derived from, it makes sense to see that probability of B given P is the probability that you are in P while you already know that you are inside of B. So, numerically, you can confirm the following. In summary, you really are using what you already know from conditional probability. The probability of B sub j given A equals to the probability of B sub j and A divided by the probability of A. It's just that when the information given to you are a couple of small pieces rather than the big picture, you get to deduce the probability that you are looking for using the law of total probability. So simple.